In this video, we introduce a brand new concept called partial fraction decomposition. Basically, you're just taking fractions apart. Let's get started. So in calculus, one of the things you're going to be having to do is take something called an integral. And when you try to find the integral of a really big fraction, it is almost impossible to do unless you first separate the fraction into smaller fractions called partial fractions. And so that's the skill we're practicing today. So we begin by looking for patterns in our denominator. We're going to factor those denominators and see what kind of factors we have. So for example, the easy case, linear factors. When I have a linear factor, that means I have a factor whose highest power is 1. So for example, x minus 4 is a nice linear factor. And if I have a linear factor, then what we're going to do is we're going to say that on top of that linear factor is some constant. And since we don't know the constant, we're going to call it a or b or c. Okay? So that'll be the game plan for linear factors. Now you're going to want to come back to this slide a lot in your notes as you're looking for what kind of pattern you're dealing with. The repeated linear factor, however, that's going to be your hardest case. I'll put a little star next to it. The repeated linear factor will be where you have a linear factor, degree 1, but it occurs more than once in your denominator. So maybe to the second power or the third power, etc. Now, what makes this difficult is that instead of just having a single fraction, a partial fraction with that factor as your denominator, you have to work your way up to it. So if you have x minus 4 to the second power, you start with something over x minus 4 and then something over x minus 4 squared. So it does become quite tedious. So imagine if you had degree 3 for a linear factor, multiplicity 3 rather. You would end up having something over x minus 4 plus something over x minus 4 squared plus something else over x minus 4 to the third power. Okay, so it gets a lot more tedious as your multiplicities for those repeated factors grows. Okay, so we'll come back to that one today, I promise. Now the next one is called the quadratic, meaning degree 2, irreducible. Now a lot of students just see the word quadratic and they don't know what the word irreducible means. Remember, quadratic meant degree 2, okay? But irreducible means you cannot factor any further. Now if I had a factor like x squared plus 4, let me grab a color here. If I had a factor like x squared plus 4, that would be considered irreducible quadratic. And the reason is because that one cannot be factored over the real numbers because it's a sum of two squares, x squared plus 4. You might think, no, professor, I've got this. Maybe I'll do x minus 2 times x minus 2. Not going to work. You get a middle term, negative 4x. Or maybe you try x plus 2. Again, you get a middle term, positive 4x. So how do you get rid of that middle term? The only way you could factor it, it turns out, if you remember from our previous discussions with imaginary zeros, is if you had two factors like x plus 2i and x minus 2i, where I was the square root of negative 1. In that case, we could factor. But when we say quadratic irreducible, we mean over the real numbers. So this is quadratic irreducible. Not to be confused with quadratics that could be factored, like x squared minus 4. That would be a difference of squares factorable as x plus 2 and x minus 2. So you need to make sure you understand what type of quadratics you're dealing with. Could I factor them further? If so, you have to do that. Otherwise, if it's quadratic irreducible, check out the pattern here. This pattern's a little bit different than the rest of them so far. This time, in your denominator, you'll just have your quadratic irreducible factor, like x squared plus 4. But in your numerator, you're going to be 1 degree lower. So instead of a constant, which would have been degree 0, we need to be a linear factor of degree 1 on top. So that would be 1 apart. So we call it like a times x plus b. So something x plus a number. Okay, so that'll be an interesting new pattern to try out. The last one, to be honest, I usually don't test you on in this course, but when you get to calculus itself, you may in fact see a quadratic irreducible which has been repeated, meaning it has a power other than 1. In that case, it's exactly like the repeated linear factors. You build your way up to it, but with the same type of numerators as you would have for a normal quadratic irreducible. So on the bottom of this slide, I've just pointed out to you that in your previous math classes, you would take two fractions which were being added or subtracted, and you would combine them by getting a least common denominator, right? And multiplying each fraction independently by what it was missing. But now what we're doing is we're starting with this bigger fraction and we're going the other way. We're trying to find out how to get the partial fractions that it came from, and that will be very helpful in calculus. In fact, if you're curious, you can click on the calculus link on this slide in the PDF or PowerPoint version of your notes, and you'll go to a website for a calculus class where they actually show you the usefulness of this. So if you want to learn it in context, that would be the best advice for you. All right, so let's practice the few different forms that we're going to be looking at today. In example here on the next slide, we have x over x squared minus 2x minus 3. Okay, and I've summarized on the top of the slide, you can look at that at your leisure, the game plan. So the first step is, can I factor my denominator? So let's take a look. If you have x squared minus 2x minus 3, that factors, doesn't it? Yeah, x minus 3 and x plus 1. So you get your two factors. Okay, so we've done step 1. Check. The next thing we want to do is we want to clear our fractions. So to clear our fractions, the way we're going to be doing that, that's really step 4, I'm skipping ahead here. In step 4 here, to clear our fractions, we would need to multiply both sides by the LCD. But if you're wondering, where did this side come from? Go back to your previous slide, right? In the previous slide, we talked about the fact that if you have a linear factor, which is what step 2 is telling you to do, if you have a linear factor, then that could be represented as a partial fraction with a constant like a over that factor. So there is the fraction representing that part. And then for the other one, x plus 1, there's the fraction representing that part, b over x plus 1. So now your job is to solve this equation. So let me erase that a little bit for us so we have some freedom. Okay, so what we're trying to do is to solve for a and b. We need to find a and b in this equation. So we need a and b. This is where all of those skills that we've learned so far in this video series on matrices and on systems of equations will come in handy. And you're welcome to use all or any of those methods you like. So what do I mean? Why am I going to need those? Well, let's take a look. If you were to clear fractions right now, you would multiply both sides of this equation by the LCD, x minus 3, x plus 1, the factored version, right? Notice that that would cancel out, if you did that, if you multiplied x squared minus 2x minus 3 in each of these places, you would cancel out the denominator on the left and just get x. And on the right, the x minus 3 would cancel, and you'd be left with a times x plus 1. And for the second term, plus b, what are you left with if the x plus 1 cancels? Well, that's right. You'd be left with x minus 3, wouldn't you? I wrote it in the wrong spot there. Here, let me fix that for you. You'd be left with x minus 3. So what we have here is an equation now that has no more denominators. That's what clearing fractions does. And you can go back to other videos if you need help with that. Clearing fractions is what it's called. Now that we have cleared our fractions, we want to do something called setting up a system of equations. And the way we're going to do that is by comparing the coefficients of like terms. This is the part that is brand new for students, so it's a little uncomfortable at first. What do I mean by that? Well, if I were to go back to the equation that we have, and I were to distribute the a and the b, look what we'd have. X equals ax plus a plus bx minus 3b. Okay, now it might be more helpful for you to think of these x's or these a's and these b's as triangles and squares. Sometimes if you think of it that way, it's easier to see what's going on. Okay, so what we're really saying here is you have one x on the left right here. And if you're going to get one x on the left, that means when you add your x terms on the right, which would be ax plus bx, they better consolidate to give you just one x. So we have an unknown amount of x plus another unknown amount of x, and together they equal 1. Okay? For example, a could be 1/2 and b could be 1/2. Or a could be 1/4 and b could be 3/4. But together they must add up to 1. So that constraint gives us our first equation. So I would say that 1, the coefficient of x, better equal a plus b. So when I add up a and b, I better get 1. That's my first constraint. Let's look at our next constraint involving the constants. On the left side, notice there are no constants. So when I add up my constants from the right, a minus 3b, they better equal out to 0 because there is no constant on the left. Now what we have here is something interesting. That's a system of equations. Now you would have probably preferred if I'd written it like this. X plus y equals 1 and x minus 3y equals 0. I could give any of my algebra students that system of equations and they would jump right in with substitution or elimination, right? So take a moment, pause your video, and solve for a and b using either substitution, elimination, or if you want to use one of the matrix methods we've been studying, feel free to use technology. You can use Cramer's rule, matrix determinants, matrix inverses. Gaussian elimination with REF, any of those is a good option. All right, what did you get for A and B? Well, that's right. For A here, since I had A over x minus 3, my A was going to be 3 over 4, wasn't it? And my B was 1/4. So let's see if that makes sense in the system that we built. The first equation said if you add them up, they give you 1. Well, that's true. The second equation said if you take A, which is 3/4, minus 3 copies of B, which is 1/4, so we'd have 3/4 minus 3/4, do we get 0? Yeah. So it is, in fact, satisfying both constraints. And here's how we really could know we're right. If we go back to the original, back up here, we would have that A is 3 over 4 over x minus 3, and B is 1 over 4 over x minus 3. That looks kind of tacky, so what could I do instead? Well, if I understand what division does, it says that if you have 3 over 4, that's 3 divided by 4, so the 4 really lives in the denominator. So what I could do instead, clean that up a little bit, is I could write 3 on top. Let's get another color, make this more fun. There we go. 3 on top, and parentheses around the factor, and 4 on the bottom. And I could do 1 on top, parentheses around the factor, and 4 on the bottom. So there I have 3 over 4 times x minus 3 plus 1 over 4 times x minus, should be plus 1, I apologize. I got too excited for my own good. Here it goes. X plus 1, there he is. Okay, you might have been wondering what I was doing, and you were right, I was wrong. Okay, there it is. We have 3 over 4x minus 3 plus 1 over 4 times x plus 1. Now, how do you know you're absolutely right before you jump into a calculus problem with these two partial fractions? What you could do is use your algebra tricks, right? You could put them back together again by getting a least common denominator. Do you, in fact, get back to where you started? Okay, if you don't have the right partial fractions. All right, now, if you're wondering, is there an easier way? The fact is, there is a little shortcut that sometimes will get you some of the answers, and other times, like this one, get you all of the answers. So let me go ahead and erase my system. You can feel free to pause and write down whatever you need, or come back to this if you need to later. But let's go ahead and make some space here so I can show you my shortcut. The shortcut would take place before you actually distribute anything. So when you first clear your fractions, that's where the shortcut could come in. So what is this shortcut? So the shortcut says, at this step here, after you've cleared your fractions, here's what you'd want to do. Excuse me. You would want to let x equal a number that would cancel out one of your terms. So for example, in this first factor, if x were -1, wouldn't that wipe away the term containing a? Because you'd get 0 times a? Yeah. So what would the equation look like? Well, it would be -1 for x on the left, and on the right side, we'd still have b next to something. Well, -1 is x now. -1 minus 3 is -4. Can you solve that nice linear equation for b? Yeah, b is -1 divided by -4, which is 1 over 4. Hey, that's exactly what we found using the system of equations. So I'm sure some of you are smiling right now. Yes, there was an easier way. You're right. It won't work for everything, but it'll definitely save you some time. What else could I let x equal? That's right, we let x equal 3. Because if x is 3, it would wipe away the term containing b. So I would be left with positive 3 on the left, because that's my x value. And on the right, I would have a next to what? 3 plus 1, which is 4. And notice we have a nice answer for a now. A is 3/4, which is exactly what we had found using our system of equations. So that is a nice shortcut that definitely works for the easy cases for all your answers, but for the bigger cases, it'll get you some of the answers, but not all of them. So if you're wondering, do I have to know how to set up the system of equations? The answer is yes. Sorry. Okay. Let's head over to another example with a different pattern. This time we had distinct linear factors, which were just a constant over each factor, but let's see what we have next. In this next example, we're asked to do the same thing. Find the partial fraction decomposition for this big fraction, x minus 1 on top, and they've already done the factoring for us. On the bottom, we have x plus 2 squared times x minus 3. Okay, so what was that first step that we did? That's right, we would set it up. So we would say, well, what kind of factors do I have? I have a linear factor of x plus 2 getting squared, which would mean I need to work my way up to it. So my first partial fraction would be the constant a over x plus 2. The second partial fraction would be the constant b over x plus 2 squared. So I've worked my way up to it. And then I have just the normal distinct linear factor, x minus 3. So my last partial fraction would be c over x minus 3. And now what did we do? We cleared the fractions. Good job. So to clear the fractions, let's see what that would bring us to here. Multiplying both sides, so every term of both sides, by your LCD, by your denominator on the left, you would get just x minus 1 on the left. Feel free to write it out if you need to. Equals a times what? Well, the x plus 2 would cancel one time. You'd still have another x plus 2, and you would still have the x minus 3, wouldn't you? What about our next term? What is b sitting next to? Well, the x plus 2 now cancels both times, since we have x plus 2 squared in the denominator, but we'd be left with the x minus 3. And finally, the c term is next to what? That's right, the x minus 3 term cancels, but you're still left with 2 copies of x plus 2. I like to write them out so that I remind myself to FOIL. Okay, now at this point you're probably wondering, can I please try the shortcut? And yes, you are free to try your shortcut. So let's go ahead and make some space here for a shortcut. For our shortcut here, what are we going to let x be? That's right, we could let x equal 2. So what happens when x is 2? Well, on the left side, we would have 2 minus 1, which is 1. And on the right side, the 2, sorry, did I say 2? I meant negative 2. Oh, goodness. I'm making all kinds of mistakes today. Let's fix that. It would be negative 2. I apologize for giving you false hope here. Negative 2 would actually be what we want to use in order to cancel out this term, right? Okay, let's try it again. Negative 2 minus 1 is negative 3 on the left, but on the right, what would we have? That's right, the a term cancels, and negative 2 minus 3 is negative 5, so we would have b times negative 5, or negative 5b. And then here, the negative 2 would cancel out our c term as well, wouldn't it? So we now know at least what b is. Negative 3 divided by negative 5, or 3 over 5. So we got one part done. Great. Similarly, when you let x equal positive 3, we get 3 minus 1 on the left, which is 2. And we'd cancel out the a term because 3 would cancel x minus 3's factor out. It would also cancel out the b term. But c would be next to what? 3 plus 2 is 5, so that happens twice. 5 times 5 is 25. So now we have c. c is 2 over 25. So at this point, we have 2 of the 3 unknowns. We could actually replace our answer for b here with 3/5. And we could replace our answer for c here with 2/25. So we know those 2 of the 3. But how do we get a? Well, that's where we have to start building our system. So let's at least get it started, see how far we have to go. So to get started, we would need to FOIL out our 2 binomials there. So we would have a next to what? Well, I would have x squared. I would get negative 3x plus 2x, which is negative x when I combine, and negative 6 for my constant. Then I would distribute the b, getting bx minus 3b. You could take your time, I'm going a little fast. And then you would have your c next to the result of FOILing out x plus 2 times x plus 2. So we get the trinomial x squared plus 4x plus 4. Okay, now you could definitely take your time distributing every single piece out, but I actually have enough now to set up my system. Let me show you what I mean. So to set up my system here, this is what I should have. For the x squared terms, do I have any x squared terms on the left? No, there's no terms, x squared terms. So I would say that 0 is the result of combining my x squared terms. So what would my x squared terms have been? Well, they would have been ax squared, so a. I'm only looking at the coefficients here. What other x squared terms? How about cx squared? So a plus c should wipe out to 0. So ax squared plus cx squared should wipe out to 0. Well, that's really good news because we already know c, don't we? Yeah, that's right. C was 2/25. So by using my c value here, I now know a. So 0 equals a plus 2 over 25. So now I know what a is. A is just negative 2 over 25. So it turns out I could stop here if I just used the shortcut to find b and c and then set up the first equation of my system by comparing the x squared terms. I now found a. So it turns out that the answer here should look like a is negative 2/25, so negative 2 over 25 copies of x plus 2. B was 3/5, so plus 3 over 5 copies of x plus 2 squared. C was 2/25, so plus 2 over 25 copies of x minus 3. And again, you could always check this how? By getting an LCD and putting them back together again and seeing if you come back to where you started. Now, if you are someone who doesn't want to use the shortcut method and you simply wanted to set up your system of equations, let me show you how you could have used technology real quick. You could have continued your system by looking at the x terms. On the left side, we have 1x, so the result should be a 1 for my coefficients of x. And on the right side, I have negative ax, so negative a is my coefficient of x. I have bx, so b is my coefficient of x. And I would get c times 4x, or 4c is my coefficient of x there. And then for the last equation, I would have looked at my constants. My constants would have been a times negative 6, which is negative 6a. So negative 6a. Notice on the left side, my constant was just negative 1. My other constants include negative 3b. And finally, c times 4, which is 4c. And so this is why I wanted to show this way to you really quickly. You don't have to do this every time. But using technology, couldn't you have written out in your calculator a nice augmented 3x4 matrix where you'd have a column for your a coefficients, your b coefficients, your c coefficients, and your constants? So the coefficients of a would have been 1, negative 1, and negative 6 for your first column. The coefficients of b were 0, 1, and negative 3 for your second column. The coefficients of c were 1, 4, and 4 for your third column. And the constants were 0, 1, and negative 1. And then using technology, if you found the reduced row echelon form, it should end up giving you a situation where you have your 1s on your diagonal, 0s everywhere else, except on the constant side. Your constant should have ended up being these numbers, a, b, and c. Okay? And so it's really nice as you can check your work that way. All right. Well, we have one more to try. This was the hardest one, so if you feel like you did not like that one, that's pretty normal. The next one's a lot nicer. So let's take a look at our final example. As usual, feel free to try it on your own and then pause and come back to me. So in example 3, it says, can you find the partial fraction decomposition for the following? We have x squared plus 2x minus 1 on top, and in the denominator we have factors of x squared plus 1 in parentheses and x minus 1 in parentheses. So what do we have here? Well, for my first denominator factor, x squared plus 1 is an irreducible quadratic. Notice if it had been x squared minus 1, you would have to factor that, wouldn't you? X plus 1, x minus 1. But this is a sum of squares. It is irreducible. So remember here what that meant for this type of partial fraction? You would need to be 1 degree lower for your numerator. So instead of a constant, you would have a constant a times x plus another constant b. So ax plus b is my numerator for the x squared plus 1 denominator. But for the second type of factor, you had a distinct linear factor. So that just meant a constant on top of it. So that's what we have here, plus c over x minus 1. At this point, you would do the same thing that we've done so far today. You would clear your fractions, getting just x squared plus 2x minus 1 on the left, and just parentheses, ax plus b, times whatever's left, which would be x minus 1, after multiplying both sides by the LCD, plus the c term times what's left next to it, which is x squared plus 1. If you got that, great job. Now, if you try to use your shortcut here, it would only get you so far. So for example, if you did the shortcut here, notice it wouldn't help you with the irreducible quadratic factor because there is no number that would wipe away an irreducible quadratic unless it was imaginary. But it would help you wipe out the first one, right? When x equals 1. So if x were equal to 1, what would happen on the left? You'd get 1 squared plus 2 times 1, which is 2. So now I have 1 plus 2, which is 3, and 3 minus 1 is 2. So I would have 2 on the left. And on the right side, the first term would cancel because x minus 1 goes to 0. But the c would be next to what? 1 squared is 1. 1 plus 1 is 2. So now we know what c is, don't we? If 2 times c equals 2, c must be 1. So already I know that c is really a 1. Well, that's fun. And then I could continue to find a and b by at least beginning my system of equations. So I would FOIL out, for example, the first two, ax plus b times x minus 1, which would have given me ax squared. It would have given me negative ax plus bx minus b, and then distributing the next part, we'd get plus cx squared plus c. And so what does that mean? Well, I could compare my x squared terms. On the left, I have 1x squared, and what are my coefficients of x squared on the right? Well, just ax squared, so a, and cx squared, so plus c. So a plus c better equal 1. Well, that's good news because we know what c is, don't we? From above here, c was 1. So plugging in c, we'd have 1 equals a plus 1. So what is a? It's kind of funky. A is 0, isn't it? Well, that's interesting. That means this part goes to 0. So we just have b over our x squared plus 1 term. Let's see if we can find b by using our next equation. Looking at the x terms coefficients. On the left, we'd get 2 as the coefficient of x. And on the right, we'd have negative a as the coefficient of that x, plus b as the coefficient of this x. Any other x terms? No, that's it. Well, again, good news because we know what a is. So letting a equal 0, we'd have 2 equals, well, just b, isn't it, if a is 0. So since we found our a was in fact 2, sorry, a was 0, b was 2, we now have answered this question. The answer for our partial fraction decomposition should have been 2 over x squared plus 1 plus 1 over x minus 1. And this is going to be what you would use in a calculus problem. You would integrate these partial fractions rather than integrating the original function itself. Again, if you'd like to use the technology to finish this one off, to check it another way, to get your constant equation, you would have had negative 1 on the left, and on the right, just negative b plus c. So you would have had for your augmented matrix, the A column would have been 1, negative 1, 0. The B column would have been 0, 1, negative 1. And the C column would have been 1, 0, 1, with the constant column 1, 2, negative 1. And your answers that you should have gotten when you do reduced row echelon form in your calculator, 1's in the diagonals, 0's everywhere else, except for your constants, which would be your answers of A is 0, B is 2, C is 1. So feel free to use technology to check as well. All right, so that's called partial fraction decomposition. I hope you enjoy it. Good luck, and remember, it's up to you now because math is not a spectator sport. Good luck. See you next time.